Hello! Welcome to yet another video in this course on group theory. In this question, there was a similar question that exists on this channel. It is a little complicated, so I thought of solving an easier problem and letting you get the hang of solving these kind of problems where you have to find out the left cosets of a subgroup of the permutation group. So it is given that our set is the set of all permutations and the operation is a combination of those permutations. So our S3 is a group of permutations of three objects. Now, since we are dealing with three objects, we have got a total of 6 elements in G. Now, the 6 is obtained by looking at the factorial of the number of objects. Furthermore, we are given that there is an element alpha which contains the description of a permutation. So let us try to get an idea about how does this permutation look like pictorially, right? So first, second and third positions, first, second and third positions. Let us assume that there is an element A in the first position, there is an element B in the second position, and there is an element C in the third position. All right. It is said that 1 goes to 2, which means that the first position element goes to the second position. So, in our revised permutation, in the permutation defined by alpha, A is in the second position. Look at the alpha. In alpha, 2 goes to 3. So the second position element moves to the third position. So B is now in the third position. And similarly, if you look at the alpha element, 3 goes to 1, which means that the third position element goes to the first position. And therefore, we get the permutation CAB. So the permutation CAB is represented by alpha. Now we want to find out, first of all, what is the subgroup generated by this alpha. Hence, what we do is we look at this representation, which means that this would contain the set of elements alpha, alpha to the power 2. By the way, alpha means alpha to the power 1, alpha to the power 3, alpha to the power 4, and so on and so forth till we reach the identity element. Now, this identity element is defined as follows. Let us say that identity element is E. So the identity element E is going to be the permutation in which 1 remains in the 1, the second position remains at the second position, and the third position remains at the third position. All right. Now let us calculate all the combinations alpha to the power 2, alpha to the power 3, alpha to the power 4 till we reach the identity element and we stop at that position. All right. So alpha to the power 2. See, alpha is already in H, right? So alpha to the power 2 would be alpha composed with alpha. Alpha is 1, 2, 2 goes to 3, and 3 goes to 1. We combine this with another such scenario. 1 goes to 2, 2 goes to 3, and 3 goes to 1. Now, the result of this, I would like to write with a little bit of space over here. Look at the red line. The red arrow takes 1 to 2 in the first permutation, and in the second permutation, the 2 is taken to 3, and hence 1 goes to 3 in the first position. In the second position, 2 goes to 3 in the first element. This element is composed with another element in which the third position, is taken to the first position. So ultimately 2 goes to 1. And finally, look at the third position, which goes to the first position in alpha, and the first position goes to the second position in the second alpha. So 3 goes to 2. Oops. Yeah. Now we find out what is alpha to the power 3. Alpha to the power 3 can be written as alpha times alpha to the power 2. Right? Because composition is associative. We can also write this as alpha to the power 2 composed with alpha. That would also yield the same result. Anyhow, let us stick to alpha times alpha composed with alpha to the power 2. This is our alpha. This is our alpha to the power 2. Now, let us conduct this composition in the same way that we had done it previously. Let us take a spacious arrangement of the first, second, and third positions initially. Let's take the red arrow, which takes 1 to 2 in the first composition alpha. In alpha square, however, the 2 is taken to 1. So 1 goes to 1. The second position is transformed to the third position in alpha, whereas the third position is moved to the second position in alpha to the power 2. Hence, the second position goes to the second position. In the third place, we have got 3, which goes to 1, right? And in alpha square, alpha to the power 2, this 1 is transformed to 3. Hence, the third position goes to the third position, or rather it remains at the third position. And as you can see, this is our identity element E. Therefore, we can write our subgroup H, which is same as the subgroup generated by alpha, as equal to alpha, alpha squared, and E. And we can possibly rewrite this in a bit more explicit way. We can write 1 goes to 1, 2 goes to 2, and 3 goes to 3 as our first element, which is E. 1 goes to 3, 2 goes to 3, and 3 goes to 1 as our alpha. And 1 goes to 3, 2 goes to 1, and 3 goes to 2 as our alpha squared. So this is our subgroup H. Now, of course, all the properties of the subgroup are satisfied over here. So we have nothing to check anymore. This is a cyclic group. We now need to identify the left cosets of this subgroup H. Now, a left coset of H in G is given by small g multiplied by H, where G belongs to the group. Now we need to identify this particular element G so that we can write the left coset. Also, the number of left cosets is equal to the number of elements in G divided by the number of elements in H by something called the Lagrange's theorem. And that gives us 6 divided by 3, that is equal to 2. So we are going to have 2 left cosets. Now let us be very clear about a particular concept that we are going to tell here. One of the left cosets is going to be H itself, right? This could be written as the identity element times H, where the identity element belongs to G. In another case, the left coset can be considered using a transposition TH, where T belongs to G is a transposition. Now, a transposition is a permutation where only two positions are interchanged. So, without loss of generality, let us consider our T to be equal to 1, 2, 2, 1, 3, 3. And we will find out what is the coset TH. Now, we remember that H is same as 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, 1, 1, 2, 3, 3, 1, 2. Right? Let us bring that over here. We'll choose each of the elements one by one and we shall get going. Let us first take our T element 1, 2, 2, 1, 3, 3. Let us compose this with 1, 2, 3, 1, 2, 3. This will give us something. Furthermore, we shall be doing the same thing with all the other elements of H. So 1, 2, 3, 2, 1, 3. This is our T element. We have got 1, 2, 2, 3, 3, 1. This is our second element from H. Finally, we have got our T element and 1, 3, 2, 1, 3, 2 to be our third element from H. Now again, the way to do this composition is same as we had done previously. Look at the first composition. 1 goes to 2 in the first, in the second 2 remains at 2. So 1 would go to 2. 2 goes to 1 in the first one. In the second one, 1 remains in 1. So 2 should go to 1. And 3 goes to 3 in the first one. 3 goes to 3 in the second one as well. So 3 would ultimately be at 3. Now let us look at our second composition. In this 1 goes to 2 and in the second permutation 2 goes to 3. So 1 would go to 3. Let us now check where 2 goes. 2 goes to 1 in the first permutation. In the second permutation 1 goes to 2. So 2 would remain at the second position. Finally, if we look at the third position, which remains in the third position in the element T, in the element from H, 3 goes to 1. So ultimately 3 should go to 1. And finally now, we look at the last composition in which 1 goes to 2 and 2 would go to 1. So basically 1 would go to 1, right? Now we look at where 2 is going, right? So 2 is the second position is moving to the first position. The first position is moving to the third position. So 2 goes to 3. And finally, when you look at the third position, which remains in the third position in T, it actually moves to the second position in the second permutation. So we get a 2 over here. And this gives us our TH to be equal to 1, 2, 3, 2, 1, 3 as the first element, 1, 2, 3, 3, 2, 1 as our second element, 1, 2, 3, 1, 3, 2 as our third element. And therefore, we can write down our final answer as left cosets are, this coset 1, which contains 1, 2, 3, 1, 2, 3. There is another coset which contains 1, 2, 3, 2, 3, 1. Another coset containing 1, 2, 3, 3, 1, 2. And in this other coset, what we get is as follows: 1, 2, 3, 2, 1, 3, 1, 2, 3, 3, 2, 1, and 1, 2, 3, 1, 3, 2. So, my dear friends, these are the two left cosets of our subgroup in the group J. One very important thing to note here is that the elements are not repeating. So, the cosets are mutually exhaustive, right? And both cosets have equal number of elements. All right. Thank you so much for watching, guys. Hope to see you soon.